So, I already made a video on this problem. This is the second video that I'll be submitting for this problem, because I really do think that my first video was astoundingly bad. And I just felt like I needed to remake it, because at the time I did this, I just got out of all my classes, and then I recorded it, and I just was talking to a wall for half an hour, and the video was just really, really, really bad. I don't recommend you watching it. But what I'm gonna try to offer here is just a little bit of a slowed down explanation on it. I'll get to it, I guess. So, the problem kind of surrounds this half pipe system, right? And in this half pipe system, you have these ramps in the half pipe system, and then you have the straightaway in the half pipe system, right? And this is 30 degrees from the horizontal. And these are height r off the ground. And then the distance of the flat is 4r. And what the premise of this problem is, you have two blocks. You have block 1, which is just a 2 kilogram, or let's just say this is the 1 kilogram object, and then you have block 2, which is 2 kilograms, right? And then in this problem, we move these blocks around. So in one instance, I'd put 2 at the top and 1 in the middle, and I'd drop 2. There's a helicopter outside my window. So I'd put 2 up here, and I'd put 1 in the middle, and then I'd drop 2, and then 2 would slide down and experience some level of deceleration due to the friction on the flat part, which happens to be 0.05. That would happen, and there'd be an elastic or kinetic collision, depending on what part of the problem we're looking at, and then you'd have to find the total distance that these blocks end up at, like where these blocks end up at on our stretch, and then you have to find how long it took for each of these events to happen. So the events is 2 dropped on 1 elastic, 2 dropped on 1 inelastic, 1 dropped on 2 elastic, and 1 dropped on 2 inelastic, and you need to find the total where they end up, and then you need to find out the time that it took for that to happen. I'm going to show you a little cute derivation at the beginning, which tells us for the inelastic collisions where these guys end up. But the algebra kind of just gets boring, and it gets really, really, really upsetting, and it gets really tiring to do it. I spent probably an hour or two messing around with the quadratic formula and getting these beautiful answers, and I summed them all up, and my answer just seemed too high to be realistic. And I just lost an hour or two just because I was really struggling with algebra. But I will go through the fun part, which is our cute little derivation, to find how long this thing takes to stop. Right, so if first of all, we start by finding the speed. We start by finding the speed if we're dropping 1 on 2 after they collide. And the first thing we need to do to find that is you need to find the energy that it has before it collides. And we know it starts with kinetic energy, mgr, because it's at the top of this ramp. And it's going to be losing mg mu k to r, just due to the friction over these this first half of our flat area. And then from here we could take out an mgr. And we could just do 1 minus 2 mu k. And we know that's our ke at collision. And then we also know that's equal to 1/2 mv squared. And what we do here is we solve for the velocity of this system, and then we multiply that velocity by 1/3, because the velocity of the system is going to be 1/3 due to its mass being tripled. So velocity after is 1/3 root 2gr 1 minus 2 mu k. And now that we know this, we convert this back into kinetic energy using the kinetic energy theorem. And then you just plug in your numbers, and it comes out to be 3/5 of a joule. That is a really small 3, I apologize. 3/5 of a joule. And if we do, okay, if we have 3/5 of a joule, minus some number of distance, and it's that distance times mu k times mg. And if we solve the equation out, it ends up taking 4r to come to a complete stop, right? And what we could do is we could just repeat this process for the other block. So this time it's just going to be 2 mgr, and I'll go through a little bit quicker this time. Minus 2 mg mu k 2l. Same premise. We'll take out a 2 mgr. We'll get 1 minus 2 mu k. And then same thing as last time. We set this equal to k equal Asian. And we set this equal to 1/2 mv squared. We solve for v. We get our v to be 2/3 root 4gr 1 minus 2 mu k. And then we do the same thing. We plug this back into the kinetic energy theorem and then solve it out. And we get 6/5 of a joule, which conveniently happens to be double this, which means we don't even have to do any algebra. We just know it's 8r. So what does this mean? What does 8r mean? 8r means that the big is going to drop down. It's going to collide with the small. They're going to go over here, go up the ramp, go down the ramp, and go to the left, and stop here, back at 0r. So just like the unit circle, 0 and 2 pi is in the same place. It's kind of the same thing. It just goes back and forth. So now the cute part's over, and now I need to talk to you about the rest of this problem, because the rest of the problem contains a lot. So what you have to do, in this problem is you have to think, okay, I put 2 here, I put 1 here. How long does this take to come down here? And then, okay, we get to here. How long does it take to go here? And also, how much does it decelerate going here? Okay, it's this collision happens. What's the speed of this block after the collision? And then what's the speed of this block after the collision? And then when this block moves and it does this, when this block goes this way, and if it goes up the ramp, or if it comes down, and if it comes back left, and then it collides again, and then it goes back up, and then it goes this way, and then it goes back down. If it does that a million times, find the deceleration and find the time that it takes for all that to happen, so you can get a total resultant distance. And it is a lot. It really is a lot of algebra that you have to do. I highly recommend that you code this. I highly recommend that you ask ChatGPT to create a program simulating a half-pipe physics, like a half-pipe physics problem with these angles and these parameters, and it would give you the answer extremely quickly. But what I found, and the thing is, right, if you crack 1,000 eggs, you're probably going to get a double yolk. And that's how I felt doing these problems. I cracked 1,000 eggs doing these problems, and I probably had a mistake somewhere in here. So these numbers are probably a little off. I was told that they are somewhat accurate, but these numbers are, if you simulate it, don't be surprised if it's a little bit off from what I'm giving you here. So the first distances, we have those 4r and 8r. And for where it stops if you drop M1 on M2, and then you have this elastic collision, that is 0.068r, and then 2.03r. And then if you drop the big on the small, the system will come to a rest where M2 will stop at 2.492r, and M1 will stop at 3.078r. 1, 2. and then 2, 1. Yep. And the times that these take. For the time for the 1 on 2, I got 8.64 seconds. And then the time for 2M on M, I got 16.30 seconds. This happens to be a lot of d equals VIT plus 1/2 AT squared, and then you have to solve the time quadratic, and then you just have to do that a bunch. And then you can take advantage of t equals square root of 2d over a at some points, like if you're at rest at the top of this and you need to know how long it takes to get down here. But it's really, it's too cute. It's two little cute setups, and then a lot of algebra. But I don't really know what to say. This problem really challenged me, just like, mentally, just like, could I keep going doing algebra even when I didn't want to? But I got a fountain pen out of it. And, I don't know. When life gives you physics problems, get a fountain pen. So, thank you for watching my video.